That tool is called an ice table. The I stands for initial. I'm writing these out explicitly this time, but in the future, I'll tend to just abbreviate these. The C stands for change, and the E stands for equilibrium. In essence, what sort of information did we have to start with, and what sort of change had to happen to bring us to equilibrium? Going into this table will then be our concentrations of our reactants and products, and everything in this table will be in moles. In molarity. Now, one of the reasons I'm writing that up here is so I don't have to write molarity again and again and again and again through the whole table. Not a bad idea, but you do want to keep in mind, particularly if you're someone who used a table like this to solve limiting and excess problems, in the past you may have been filling in numbers in a table like this that were moles instead. So do keep those units in the back of your head as you work through this problem. So, what was our situation initially? Well, we're imagining that this solution we were told about was what someone made in a lab. They measured out 0.05 moles of acetic acid and added it into a liter of water. I'm oversimplifying a little bit. Obviously, you'd go to exactly 1 liter. You guys remember how to make solutions, so I won't go into too much detail. But fundamentally, this is our initial concentration. We're also going to initially say that our amount of H plus is 0. But wait, you might be saying, didn't you just tell us that water autoionizes? And that's true. But in this case, we know that the amount of H plus we're making is 10 to the negative 4 molar, almost 10 to the negative 3. And by comparison, our neutral water we started with would have had something like 10 to the negative 7 molar. That is pH 7. So in this case, this is an amount small enough that we can often get away with being a little bit lazy and calling it 0. Last but not least, we know that there is no acetate in solution. Okay, what else do we know? Well, we know that when we were all done, when we were at equilibrium, our concentration of H plus was 9.6 times 10 to the negative 4. If that's the case, then our change to go from 0 to 9.6 times 10 to the negative 4 must have been plus 9.6 times 10 to the negative 4. Now's the time that we can put this chemical reaction equation we have to work, because that equation is telling us something very specific. That equation is saying that every time 1 mole of acetic acid reacts, it's going to produce 1 mole of H plus and 1 mole of acetate. So, if we formed 1 mole, or in this case, 9.6 times 10 to the negative 4 moles of H plus, that must have meant that we also formed the same amount of acetate. Now, if we started with 0 acetate and we're now ending up with some amount, well, the amount we end up with must be whatever we got based on this change. Likewise, if we made this much H plus, the only way we could have made it was by consuming acetic acid. So the change in our acetic acid must be minus 9.6 times 10 to the negative 4. So this is 0.050 minus 9.6 times 10 to the negative 4, right? Well, let's actually write this guy out. So that would look like 0.00, negative 1, negative 2, negative 3, negative 1, 2, 3, 4. If we subtract that, one of the things you might recall is that we only keep the least significant figures in our number. So in this case, the amount we are subtracting here is so small that it is insignificant. And I mean that in the literal mathematical sense of the term. It is truly not significant how much we removed. If you want to get fancy, you could remove it. What we tend to observe is that when you do your final significant figures for your solution, that is for your answer when you're done, it tends to not matter. So it's often, but not always the case, that we can say that this is going to behave very much as though it didn't actually dissociate anything at all. The number just doesn't change by very much. OK, so we're pretty much ready now to plug these numbers into our KEQ expression. So let's do that. I'm going to erase myself a little bit of space to do that up here. So our concentration of our acid our concentration of that conjugate base, and our concentration of the conjugate acid, the acetic acid. Make sure that you can plug those into your calculator. Scientific notation sometimes requires a little bit of a refresher. And once you've done that, calculate the KEQ value for acetic acid. Now, checking my notes, I find that is 1.8 times 10 to the negative 5. The KEQ value for a weak acid gets a very particular name. That name is called Ka. It's the acid dissociation constant. So we can now call this Ka. It will probably not surprise you to learn that bases also have an equivalent value called Kb that we'll be looking at a little bit later. These Kas are really useful because they are a number that tells us exactly how weak or strong an acid or base is. Now, you can see here that this number is already 10 to the negative 5. When we have numbers that vary by many orders of magnitude, we'll often switch them over to something like pH. So we'll instead typically be using pKa values. We'll look at some calculations related to those up next. While you're waiting, please take a look in your textbook to find the table of pKa's for a variety of common acids.